Well, I think we can start. So, our today's speaker is Professor Vladimir Rubtsov, and his talk is everything you wanted to know about the modified Bessel equation, but we're afraid to ask. And Volodya, you are welcome.
Thank you very much. First of all, thank you very much for this invitation. It's always a pleasure to be with you and to speak. And also, I want to warn you. Unfortunately, it is possible. I hope it will not the case today. Yesterday, I gave a talk also in a Russian seminar, and in the middle of the talk, something was wrong with the internet connection. So I was interrupted, seriously interrupted for, I had to reload everything, and it was not clear what's the reason of this interruption. I think that it is local problem because the day before they had a serious current break here at IHS. So if something wrong today, I'm terribly sorry, and just wait, I will do my best. But hope today, up to this moment, everything was okay. So let's go. First of all, I should explain the title, and I should explain the reason why I wanted to give this talk and the form of this talk also, because it is double twofold. A big part of this talk it is handwritten, and some part of this talk it is just my slides of talks which I prepared, for example, for yesterday and before. I should also beg my pardon if you will find the first part of my talk banal, trivial, and I would say on the level of first 2 years of the university. But to my shame, probably it is my personal shame, a few years ago when I started to work on this problematic, I discovered that I know nothing about many standard, like people say, things from the standard classical course of analysis. For example, I knew nothing about Bessel functions. I heard the name of Bessel in the Fourier theory course. I knew the Besselland inequality and so on. And I knew that there is an equation and there is some special function which is the solution of this equation. What was this equation and what was this function and what kind of theory around? I had no idea. It was just big. And it was terribly shameful because I suppose that big part of my life I was close, at least close to differential equations, and I knew nothing about very elementary differential equations. That's why I want to maybe to be more detailed in some trivial part of my talk. So what's the title? The title is a reminiscence of a very old paper of British mathematician R. Scott, which is called The Land Beyond Bessel, survey about special functions. This paper was written in 1980 in lecture notes of mathematics. It was a special lecture notes devoted to some conference, British conference, ordinary and partial differential equations, very old-fashioned conference, very old, typically British participants, and the subject also very standard. And from this paper, I understood the following, that classical studies of differential equations, which started probably with the name of Bernoulli and Euler in 18th century, they were very really advanced people, and they understood many things, but they just they were solvers. They were not creators of something beautiful picture. So they created methods, but didn't created the general picture. And the first half of 19th century, following to this to this paper of Arscott, he argued that physical ideas and physical intuition dominated and prevailed over differential equation technique, which we like so much. For example, they were very advanced in solution of concrete problems, say potential theory, wave problems, and then they create Legendre and Bessel for different type of domain, for spheres, for cylinders, etc. And only after appearance of papers of Gauss and Riemann, and also Cauchy participated, but mainly Gauss and Riemann, they brought together all these technically, physically motivated and technically advanced results, and they started to create some kind of general scheme. And the main result of this creation was, of course, theory of differential equations with regular and irregular singularities. So in particular, Gauss was inventor of course, some examples of these hypergeometric functions. They were known to Euler as well, but Gauss introduced the solution, Gauss hypergeometric f to 1 function, which is the solution of Gauss hypergeometric equation, which has 3 singular points, 0, 1, and infinity, considering these points on a Riemann sphere P1. Now, I want to say that when people created this theory of regular and irregular singular points for second-order differential equations, then they also immediately started to develop the links between these. And the good motivation for this link was different degeneration models, one equations into another. This is a scheme, now is a well-known scheme, how hypergeometric Gauss equation degenerates when the singular points coalesce or collide. Say, these simple poles, they try to glue one with another. And then immediately Gauss equation gives the Kummer, and Kummer equation gives a Bessel equation, or in another way of colliding gives you Hermite polynomial solutions. And both Bessel and Hermite, or which is also Hermite solutions, they also associated with so-called parabolic cylinder case. So they gives the Airy function and Airy equation, which is quite popular because of the first serious study of so-called Stokes phenomenon. But what the procedure, this coalescence? Analytically, it is not very difficult. Just let's consider this Gauss-Kummer passage. The Gauss-Kummer passage, it is just a change of variables. We replace in this hypergeometric equation variables z by u times epsilon, which will be a parameter, and the constants which enter in the equation, beta replaced by 1 over epsilon. Then this simple change of variables gives the following equation. And this equation, this equation has all coefficients in front of derivatives holomorphic in this epsilon parameter. So they are holomorphic in the vicinity of the epsilon equal to 0. And when we go to 0 with epsilon, then this we obtain from Gauss hypergeometric so-called Kummer degenerated hypergeometry and hypergeometric equation of the following type, you see. So geometrically, what it means? It means geometrically that we have, say, singular point of Gauss equation 1 and infinity, and this singular point 1 goes to infinity when epsilon goes to 0. So we obtain from poles, we obtain irregular singularity. What was my motivation? I'll just try to come back to my talk, which probably I gave here few years ago, and poor Renia probably attended this talk, this subject talks many times. So this conference diagram for hypergeometric degeneration, in fact, geometrically means the following. We can interpret this data of associated with solutions in each case as a so-called monodromy surface. This monodromy surface is a sphere with 3 points for Gauss case, and cylinder with 2 points with smooth border and with border with some singularities. These singularities appeared as a result of this conference procedure. So we have this idea in our joint paper with Leonid Chekhov and Marta Mazzotta, how to imagine this geometrically this conference coalescence procedure. So if you have two smooth borders around simple singularities, then you can, in the language of hyperbolic geometry, it is very explicit, and analytically you saw it. You saw these formulas even also very explicit. But geometrically, you can imagine that these two smooth borders, they goes one to another, and as a result, you obtain only one border, but this border will have two infinite cusps, like we call this object. This object obtained if you imagine that this material of the surface, it is a kind of chewing gum-like rubber, and you start to pinch this and trying to keep the hyperbolic area conserved, go to infinity. So you just like a bad boy who has the chewing gum in his mouth, just go to try to take this chewing gum as long as possible. And at some point, of course, this breaks, and then this border becomes only one instead of two. And as a result, these two cusps gives you geometric interpretation of Stokes phenomena, which I will not discuss it in the detail because today it is not main object of my interest. So this geometrically related to Stokes phenomena, which replace monodromy data studies in the case of irregular singular points. And then we have continue these chewing gum operators. So white arrows, I described these white arrows, it is just a colliding of borders. So as a result, you can collide these two borders, and then you obtain one border, but with four cusps, because this operation always gives you even number of these cusps when you use this chewing gum principle. But also there is a second operation, which is also a kind of chewing gum operation, but not a colliding of borders, but colliding of cusps. If you have even number of cusps, it is important that you can't eliminate one cusp. But if you have even number of cusps like this, you can make colliding these two cusps in one. And this gives you the Bessel cylinder with one cusp. I will not speak about compactification, about decoration, because decoration, you have infinite lines. So these infinite lines, you should do something with this. So you can just glue to each cusp or cycles in hyperbolic model. So you will have geometrically nice and handleable object, I mean, treatable object. So this is the four cusps in the one border, and this is the three cusps, sorry. And this is the three cusps in one border, which correspond to this area equation data. And this picture, I took this picture from the paper of my beautiful former PhD student, Oleg Lisovy, and his co-authors. When they used our diagram with Leonie and Marta, this is our diagram and with Leonie and Marta, but what they did, they considered this data from hypergeometric low level. This is the data of higher level. It means this is the monodromy data of so-called Penlevet transcendence. Sphere with 4-point P6 and P5 with the same principle, but for Penlevet 6. This was a result of our first paper with Leonie and Marta. And this paper, they interpreted our result in the following way. They took the hypergeometric data, and this hypergeometric data, they used to create our Penlevet models. You see? So they took two hypergeometric pantaloons and glue by a common border, and they obtained Penlevet 6 monodromy data. They took Whittaker, they called it Whittaker, it is Kummer, it is just the same equation in different parameterization. You can have different number for the solution. So they called it Whittaker, and Whittaker, it is a special type of Kummer hypergeometric degeneration, as I will explain very soon. So this Kummer or Whittaker, you can glue with Gauss and you obtain Penlevet 5. And these three data surfaces, they interpreted like the case of solvable Riemann-Hilbert problems, which they considered in the conformal field theory reasons. I will not go into these details. I just want to say that it is very nice geometric interpretation, and it is very nice correspondence between high level of Penlevé confluence diagram and low level the hypergeometric diagram. Now, just more down to the earth things. What these solutions of Kummer and how this degeneration, how this confluence of solutions of Gauss equation gives the solution of Kummer equation. This solution is given, oops, sorry. What's happened? Ay. Oh. I'm sorry.
Да, Володь, многие знания, многие печали.
No. Oi. Oh. It's old, very old machine. It's not. No. What's happening? I don't understand what's happening. Yes.
Ты или файл помнишь, ты поищи.
No, it's okay.
Я бы не сказал.
Oh. You will see what you will wait. Okay, so let's come back to this solution. This solution looks as follows. You take the generation of solution of Gauss, F21, and the parameter beta in the formula for series which gives this solution. This is a series whose coefficients are so-called ratio of Pochheimer symbols. This A sub n, B sub n, and C sub n. They are so-called Pochheimer symbols. It is just a kind of it's a kind of ratio of gamma functions which continue to any value of argument. And this Pochheimer symbols ratio, when beta goes to infinity, it corresponds to this degeneration of the equation, gives you this function, which also looks like F21. It is usually denoted by big phi or F11, and they call Kummer degeneration hypergeometric function. Also with two Pochheimer symbols, which depend only of two other parameters, and B tends to infinity. So we have a good solution of our Kummer second-order equation, but our equation has an irregular singularity after this colliding. So the second solution will not be so good. And this second solution indeed...
Volodya, I'm sorry. Can you remove this plate with colors and pencils? Oh, thank you.
So this second solution is not so good like the first one. This solution usually called confluent trichomy hypergeometric solution. And this solution, it is not an entire function, and it contains a logarithm. And this is the result of so-called Frobenius method, how to find the fundamental solutions of the second order Kummer equation. And this trichomy function has this logarithmic term, and then it has this series in degree z. Of course, this expression which I used, it is not the very correct way to express the second solution. Why? Because to say the truth, and I was very surprised to know all these details, when you write second independent, linearly independent solution for this equation, that this naive and nice form doesn't exist for all values of parameters A and C. You should eliminate integer values of parameters, positive integers of C, because it will be the poles, etc. You see, you have this gamma function in the general expression of this expression is more complicated. It's combination of first entire solution with this gamma function ratios, but don't think that this it is linear dependency between phi and t. They are independent in the way, in some way, because this more common and more complicated expression, they are not the same. You see, they are not the same solution. They are solutions with different values of these parameters A and B and A and C. So you see that this procedure, we can now go further, and we will go to the Bessel case, which is our aim in today. And Bessel solution, it is solution of the equation which even me, I was ignorant, but even me, I knew it. This is a standard second order equation. It has a singular point in the origins, and it depends on one parameter, mu, complex parameter mu. So we can apply this Frobenius method and check what kind of singularity we have in this origin z equal to 0 for this equation. So checking this limits ratio of coefficients of our second order equation, like in general procedure, our coefficients are very simple. We see z square and z square minus mu square, and taking the limits of this expression, z times ratio and z square times this ratio of coefficients, we see that these functions, they are very good analytic, so we can find solution by Frobenius methods in series. The question, when we write this solution form of series with z to r as a common factor, then there are some solutions. What r we should find, what the convergence radius of this series, and do we have some recursion relations on the coefficients to write the solution. All these questions we can easily solve, and we obtain the first entire solution, which is called first Bessel function G. This is just a G0, and this G0 is a series Taylor series with sign and alternating sign. And second solution, as in the case of Kummer equation, contains this logarithm. So we have this second Bessel function of degree 0 and second kind. These phenomena, of course, continue for all values of degree. We can write entire series for first kind Bessel function, and degree nu. It's any degree, not necessarily 0 and not necessarily integer. It is also admit complex values, and it is important because to write independent fundamental solutions for Bessel equation, we need more complicated second kind Bessel function k nu, which depends also which contains two parts, this logarithmic part and this series. And I would like to say that I'm almost will. It is maybe not the last, but at least once I will go to the second kind of Bessel function. I will speak today mainly about first kind Bessel function. And moreover, most part of my time I will speak about Bessel function of degree 0. So that's why I go to the most simple type of Bessel equation when I take nu equal to 0. So this is Bessel equation with nu equal to 0. And this equation solution, we can write in integral form. This I0, it's modified equation, modified Bessel function of the first kind. And there is a logarithmic analog of it, which also can be written in integral form, but not in the form of residue like this in Cauchy form, but as an integral. It's a multivalued function, and to write this, we need to put conditions on the argument of our function z. Now, why we interested in this object, and why I started to interested in this object? Not only because it is interesting how to solutions behave under degeneration and under confluence. There are some physical motivations. I will describe very briefly, just to tell you something maybe interesting, maybe what you don't know about this Bessel. Everything which I told before, you know probably very well. It was me who didn't know it. But this is really very interesting. There is a problem which is called Bessel momentum problem. This problem appeared in 2008, I suppose. And the problem is the following. Let's consider the matrix Bm with index 2 times A plus 1. And matrix entry of this matrix, which correspond to indices I and J, they are some constant, which is irrelevant for our story at the moment, integral from 0 to infinity of modified Bessel function of degree 0 in degree I, and modified Bessel function of second kind of degree 0 in degree 2 times L plus 1 minus I. And also we have this measure factor Z2 times J minus 1 dz. I and J, they are between 1 and L, when L is a half of this index. So we have L times L matrix, and this matrix is called matrix of Bessel momentum. That's why notation BM. And two physicists, but they are even better mathematicians than many mathematicians, Broadhurst and Roberts. Unfortunately, Roberts died. And Broadhurst seems to recently. They made the following experimental conjecture. They conjecture that after some verification with Sage, with manipulators of type Maples and many other computer experiments, they suppose that there is a quadratic relation that if you take this Bessel momentum matrix and take conjugated matrix, transposed matrix, then there are matrix D sub K and B sub K. Matrix B, it is just explicitly described matrix which has some hypergeometric nature. The entries of this matrix may be explicitly expressed as a product of factorials times Bernoulli numbers, very explicit matrix D. And matrix B, I speak about right-hand side. And matrix D, it is just some matrix with rational entries. They computed it for each small value of size for this Bessel momentum. Why it is interesting, you will see just in a few seconds. Then mathematicians came to this problem, and Frisand, Sabat, and Yu, they proved that this conjecture, in fact, is a theorem. It's true. And moreover, they enlarged this not only for odd index 2 times L plus 1, but for any index, even indices as well, which is a little bit more complicated quadratic relation, but the same. Why it is amazing? It is really amazing because as a toolbox, they used Deligne-Hodge theory for local systems with regular singularities, or just instead of local systems, you can imagine some flat connections, so differential first order linear systems with irregular matrices. And Deligne developed the theory of such differential equations. And as a first and non-trivial example, he considered this Bessel equation and Bessel connection related to this modified Bessel equation. Why this matrix is important for physicists? Because there is another observation. This observation I knew from Pierre van Hoff, and he said that there is some special Bessel momentum matrices, such that special matrix element I0 degree 1 and K0 degree L plus 1 with measure ZDZ can be expressed in terms of integral which integrated by L-dimensional space by positive coordinate patches of L-dimensional space xi bigger or equal to 0 with a measure which is the historic measure. It's a product of dx over x. It's product of d of log, and then this integral, it is a kind of integral from the fraction and denominator of this fraction, it is Laurent polynomial in x1, xl, of this special type. Such type of Laurent polynomials, they were known in toric geometry. If you take here, it's -1, but if you take some parameter, you have a family of hypersurfaces in toric space, and these hypersurfaces sometimes have very good geometric properties. They are called Landau-Ginzburg or Fano toric varieties, and some of them can be compactified to good Calabi-Yau manifolds. I will probably speak about it a little bit later if I have time. So this my Landau-Ginzburg potential. So this formula and many other formulas, they I mean this Hermann-Hof formula came from another physics motivation. This another physics motivation is not mathematically oriented mirror symmetry and the Landau-Ginzburg and so on, but very down to the earth question: how to compute so-called Feynman integral. When we were young, we probably younger people maybe don't know it, but when we were young, it was a very popular subject which was called topological study of Landau singularities. So in the scattering, when physicists computed scattering amplitude, they computed so-called S matrix. Matrix elements of S matrix can be expressed in terms of Feynman integrals, and these Feynman integrals, they contain in denominator so-called propagators for this scattering kinematic of particles, and these propagators, they have special types. They are discriminant type, and this discriminant type define very complicated singularities. So to compute this integral, you need to study homology, and because of technique which was developed by Pham, Froissart, Fatiadi, French mathematicians, and many people after. And at early 2001, 2000, maybe even in the 90s, people understood that these Feynman integrals with these Landau singularities reduced to computation of so-called period integrals. These period integrals, they are exactly this right-hand side of Hermann-Hof formula. And then it is interesting to study this matrix of momentum and the different products of Bessel functions. That's what we understood with my colleague, with Ilya Gayun, a young colleague, and my elder colleague, Duke van Straten, that if we take Bessel degree zero products in various forms, they are not Picard-Fuchs equation. I mean, this Bessel equation, and we don't have a good hope to have Calabi-Yau variety in the right-hand side. But there is some substitute. We discovered that the corresponding kernels, which I will describe now, they are satisfied to some kind of Picard-Fuchs equation. And it was the main input in what I want to tell you. So the second part of my talk, of this discussion, it will be discussion of these kernels in this simplest case, and why these kernels really gives the genuine Picard-Fuchs-like equation, and why it was absolutely as a byproduct, unexpectedly, the singularity lossy of these kernels. They are related to theory of n-valued groups of Buchstaber, Ries, and other collaborators of Buchstaber. These n-valued group structures in C, CP1, and the symmetric products of this. So the main object of my study is so-called multiplication kernels. So let's suppose that we have a differential operator, whatever. I don't want at the moment to be more precise, because in future I will be very precise, and differential operators, they will be exactly the operators we discussed before. And this differential operator has eigenfunctions psi with eigenvalue lambda. If we take this eigenfunction in two different points, x and y, and take the product, and we so lucky that we can find the function k of x, y, and z such that the product expressed as a integral of the same type function in the point z with this k function as a kernel, when integral over some cycle.
I'm sorry. The order of L is arbitrary.
Sorry, order of L at the moment. At the moment, I don't care about it. At the moment.
Okay, okay.
I just want to say that the main philosophy is the following: if we have the good function phi, which satisfy to this eigen problem, linear eigen problem with operator A for some eigenvalue lambda, then it is possible if and only if it satisfies to this multiplication kernel integral equation. And sometimes integral equations, they are much easier to study than differential. That's what very simple philosophy, which in fact this philosophy came from, if you want, from elementary algebraic geometry, but I will not discuss it today. Because I discussed it in my previous talks. I spoke about relation to Abel and non-Abelian version of Abel's theorem. So what I want to show you how this multiplication kernels philosophy applied to n-Bessel or Pn-1 quantum differential operator. This operator, it's operator of nth order. Usually I will use this notation theta for logarithmic derivative. Theta, it will be logarithmic derivative. So this equation, it's equation in theta to n psi minus lambda x psi equal to 0. So it's and in the simplest case, n equal to 2, we can recognize that it is exactly our fellow modified Bessel equation. It is not exactly modified Bessel equation, because modified Bessel equation, it is this equation theta square minus z2, not if you take lambda equal to 1, it's not x, it's z2. But after this simple change of variables, I wrote I in the parentheses because this I you need to go from the initial normal non-modified Bessel. If you take G0 and then you take this change, then you go first to if you don't you just have I, you have modified Bessel, and if you have this 2 times square root of argument, you will have our equation n Bessel. It's our algorithm. We called it n Bessel. It's our algorithm. Now I explain why it is quantum and how it's related to quantum cohomology. Just very briefly, using probably you know, and Zhenya again probably knows it. It's much better. So let's consider this equation, which people call quantum equation. It's an invention of Sasha Gvintal. I introduced this equation with a constant parameter h bar, which is a Planck constant. And in the case of n equal to 2, this equation was known from 19th century under the name of Stokes equation, because Stokes wrote this equation when he invented the Stokes phenomena, because this equation has second singular point in infinity irregular, so it's what the object of Stokes studies. And in our century, people call this equation very often Klosterman operator or Klosterman equation, two Klosterman operator or two Klosterman equation, because there is a things which I have no possibility to discuss in this Deligne approach to proof of Hodge Weil conjecture, and when he developed this Hodge theory with irregular singularities for local system, he discovered correspondence between such connections and so-called Klosterman exponential sums in number theory over finite fields. And this correspondence between Bessel connections and Klosterman sums, people in number theory used very helpfully. For example, in this proof of quadratic relations for Bessel momentum, these mathematicians, they heavily used ideas from number theory over prime number field. So I will use our name. Our name is to Bessel, not Klosterman, not Stokes. And I explain how it relates to quantum cohomology. First, what quantum cohomology? It is just a modification of cup product in the usual cohomology. Let's consider the ring, cohomology ring of P to n minus 1 of this projective space. And as a vector space, this vector space generates by the it's a vector space with basis 1 c to n minus 1 generated by the generator C of second cohomology group. So this cohomology ring, it is just C generated this. You have this polynomial. Finite polynomials cutted by nth degree of this plus C. So this is the standard description of cohomology ring of Pn minus 1. Now, to have quantum cohomology, you just take the same space as a vector space, but the product you deform. And you deform this product in such a way that you use this coordinate z, like deformation coordinate, and the condition c to n equal to 0, you replace by condition c to n equal to z. And then you obtain the object which is called quantum cohomology. Quantum cohomology, I will not describe this deformation of multiplication with this h, but I want to say how it relates to our equation. it was again, I should attribute it to Sasha Giventai. In mid-90s, he just considered our n-Bessel equation with this parameter h, and he discovered that one can formally apply Frobenius procedure and to find fundamental basis W0, Wn minus 1 for this equation, and using this Frobenius basis to write what people now call Givental G function. This Givental G function is a combination of function from this Frobenius basis for this equation with degrees of cohomology classes of element C in H2. And this function, evidently analytic in this origin z equal to 0, so we can write the series for this function in this form. That's what Givental this Frobenius form, and the coefficient explicitly relates to C. Coefficient explicitly relates to C and to this Planck constant. So this, of course, having in mind the condition that C2n in usual cohomology class equal to 0, we can verify that this function G, like Givental check, satisfy our equation. So it's one example of good equation. But of course, this is not usual function. This function, it is a function which defined on H2, depends on the class C, and takes value in cohomology ring or whole cohomology ring. Well, we should be also remark that if we write this function implied some necessity of logarithm, because to understand what is z to c over h, we need just to use this logarithm representation, and so it's slightly, strictly speaking, it is a function from two cohomology to ring cohomology. It's multivariate function, which was irrelevant when you consider this solution of our equation. It is good solution, but when you consider it on the level of cohomology, it is multivariate. Okay, so this is the second object, and also there are two interesting things which I definitely have no time to discuss today, but I'm sorry, I spoke about them last time when I spoke in this seminar. I spoke about Buchstaber formal laws and polynomials which define these formal laws, and they relate to the first part which we discussed, because they are very, very similar. In fact, there is a strict identification by some kind of Möbius transformation with so-called generalized Kontsevich polynomials. And these generalized Kontsevich polynomials, I will show you the simplest of them. They relate to this multiplication kernel formula. And
Volodya,
yeah,
question. So, but what is this multiplication kernel? What is K explicitly?
each time you will see what is
in this particular for Bessel. What is K?
for this equation.
For Bessel, for this equation, yeah.
I will show you. Just a moment. This
okay.
Don't go ahead. Okay, that's the idea of this multiplication kernel of again goes back to this some relations between hypergeometric functions. This first such relation is known since 1828 under the name of Clausen duplication formula. So you remember this Gaussian 2,1f function. If we take this function with parameter a, b, and parameter c is a combination of a and b, then the square of this function can be expressed in terms of Gaussian function f2, f32, and the parameters, this function has 3 Pochheimer symbols in numerator and 2 Pochheimer symbols in denominator, but they are linear combination of a and b, and the arguments are the same. This beautiful formula, Clausen obtained it, and he was so excited that he just called his paper in Krell. He called it by this formula. The paper is called square of 2f1. He just wrote the formula. Okay. What is related to our Bessel story was the second multiplication formula, which was written by Schläfli. Schläfli, it's a Swiss mathematician who worked in Basel, and he considered confluent hypergeometry. It is the second confluence which goes from Kummer to Bessel. So this is a 0, 1 hypergeometric function. There are no it means that there are no Pochheimer in numerator, and there is a Pochheimer of n over 2 in denominator. And if you take the argument nx over 2, then you have the following product which Schläfli obtained by hand, and he expressed it in terms of integral of the same type degeneration function, but with argument. I wrote this more or less modern form of the argument, which I will try to explain from the point of view of spherical functions. But Schläfli just made direct computations, and it means that this kernel is encoded in this function. You can write maybe it's better to say that it's encoded in the measure and in the function. Interesting fact, which probably also I should mention, that this formula for different values of n gives you different addition theorems. For example, or multiplication theorems. For example, if you take n equal to 2, then you have a very simple cyclic formal group, which we will discuss under the name of addition theorem for Bessel function. And if n equal to some other values, we have no cyclic formal group. But we have a kind of coalgebra structure on the functions which enters in this beautiful formula. So it is also have a deep algebraic sense. It's commutative algebra, but anyway. For the case of n equal to 2, you can rewrite this formula, and it was done by Sonin and Gegenbauer, also mathematicians in 19th century, more or less a few years later to Schläfli, but they didn't know about his work. And they wrote this in terms of so-called usual Bessel function of degree 0. And they wrote it in classical multiplication kernel form, like I showed you before. Now, what is the kernel? The kernel here is 1 over square root of this symmetric quartic expression, and the z dz is the measure. So this kernel is z over this quartic. And that's what people called Sonin-Gegenbauer formula. For us, it was very serious motivation to study Bessel equation for not only for n equal to 2, but do we have some good property for such products of Bessel function, and what consequences of these good properties if they are. And another type of this product, it is again another answer to Zhenya question. It is so-called D2 or small a priori equation. In fact, it would be nice to explain why it is called small a priori, because this equation was used by a priori in his proof of transcendency of zeta function in odd integer points, zeta of 3, zeta of 5, etc. But he used not exactly equation, but corresponding recurrency relations. And I don't have intention to go to these number theoretic aspects. I just want to say that the corresponding to this recurrency equation has the following form. Let's take cubic f with pre-term equal to 0, degree t coefficient equal to 1, monic, and a is just coefficient in front of t squared. Then we obtained one of the a priori recursion for such equation. We put this cubic f between two derivations and consider the eigenvalue problem for this second order equation. Then solutions of this eigenvalue problem phi lambda of x, phi lambda of y, in product gives you the following. They give integral. This integral you can write also in kind of residual form. I don't want at the moment to precise what you need to integrate of this function in point z, and the kernel, it's 1 over square root of p x y z. And this p x y z, this was what people call now Kontsevich polynomial. That's what I showed you at the end of the previous slide. And this Kontsevich polynomial, it's a square quadratic polynomial in parameter t, which you obtain after subtraction from my cubic. And I want to stress that it's monocubic, and then you subtract product of t minus x, t minus y, t minus z. So they some again monocubic with t cube in front of t cube minus 1. So after subtraction, the term t cube disappear. You have a quadratic expression, and you can compute determinant of this expression in t. Then you have a function of x, y, z, and this was Kontsevich polynomial. Now it's the most amazing and difficult part. I just briefly explain why this Kontsevich polynomial was interested in number theory and in Langland's program. So Kontsevich, in his paper 2007-2009, it was appeared in 2007 in Archive and published in the book for 70th birthday of Yuri Manin in 2009. He wanted to make explicitly the Hecke operators for Lagrange correspondence. In the case of SL2 local system on P1 over field of prime characteristic P minus 4 points 0, 1, T, and infinity. But everything over phi P, phi mod P. It's important. So he considered a little bit more general point operator. This operator, like I showed you for a priori, so it's DFD, but now it contains three terms C and also all coefficients A, B in front of T square and T. Then we have a cubic polynomial, and this cubic polynomial gives you such operator. And then this polynomial enters in the following interesting answer to the question which Kontsevich answered after, I suppose, Drinfeld posed this question. So Drinfeld had a master student, Tiruji Thomas, and later another PhD student with Heinlot and Duke van Straten. They corrected a little bit what I will tell you, because what Kontsevich proposed, it was not exactly the formula which works for these Hecke operators. So over finite field with prime characteristic P different from 2, let's consider the operator H sub x for it's a matrix P plus 1 times P plus 1 with coefficients with entries in my field, and matrix element in the point YZ. So these are also element from F mod P. Is computed by the following formula. We take 2 plus number of solutions of the following equation, a number of squares W such that W square equal to some polynomial. And in fact, as I told you, in fact, in some cases, in some choice of parameters, you should add some correct term. Kontsevich just write this polynomial. And he checked that generically it is enough, but for some, these 4 points, they can have different parameter T and so on. For different choice of this, you should add some correction terms, which needs the boss in his thesis and Tiruji Thomas in his master thesis, they wrote. But Kontsevich didn't do it. He just checked that if he defined this matrix and this operator H sub x, then in two different x and y, these operators always commute. So it is a kind of miracle, and he proposed this like analog of Hecke operators. So they generate some algebra, and this algebra, of course, has a structure constant. So the question was to compute the structure constant. These operators act on functions, of course, on this P1 over phi mod P. And there is the following algebra structures where this operators enters like a structure constant. So this eigenvectors, which very similar to what's happened in complex Lagrange correspondence as well. You have some operator, you have vector V, you have eigenvalues V sub x, and these eigenvalues satisfy to this algebraic relation with this structure constant. So we have a kind of multiplication problem with the kernel given by these KK operators. And it is a miracle that in 2019 to 2021, Ettinghoff, Frenkel, and Kazdan, they made this hint explicitly, namely what Kontsevich proposed, like Hecke algebra coefficients for the case of P1 over Fp over Pc, they compute real Hecke operators. They constructed Hilbert space, they constructed scalar product, and then they wrote the kernel. And this kernel is a determinant of some polynomial, which is a generalized Kontsevich polynomial. And it is very, very explicit. In fact, all such polynomials, they relate to some cubic, so there is a elliptic curve behind it. Okay, there is also this motivation which comes from multivariate group, and this I will not, I have no time to discuss. This is the papers and books which you can use if you are interested to read more. It's a beautiful book of Watson about basic functions. There is absolutely fantastic book of now Vilenkin, special functions and the theory of group representation, when there is a general theory of such product formulas for spherical functions, and Bessel formula is a partial case of it. And there are some papers which our paper with Duko and Ilya, just I hope we'll submit it in 1 week, because we just checked the last things. And with Buchstaber and Ilya, it is a little bit different part which relates to this formal group and two-valued group story and Kontsevich multiplication formulas. It is still in progress. Okay. Joseph, how much time I have? Because I want to ask you what you expect from me. Joseph.
Sorry, I didn't switch on microphone. So I think till 9 Moscow time. So it is what is it? 23 minutes.
Okay, then I will try to explain this motivation which comes from mirror symmetry, and you will see also something interesting for the case of my Bessel operators. So one of the motivations was the study so-called Calabi-Yau differential operators. This Calabi-Yau differential operators, I will use this standard notation, which is called sometimes Euler operator theta for logarithmic derivatives instead of usual derivative. And this is a Monique operator with respect to this theta. And coefficients of these operators, they are polynomial. And what is very important, that the origin is so-called Moon point. Moon, it means maximum point, maximally unipotent monogamy point t equal to 0. I'll just remind what is it and why it is important for me. Such operators usually appeared in the following situation. You have a Calabi-Yau variety, and you have a family of Calabi-Yau parameterized by P1 with parameter T. And on each variety, you have a top form, holomorphic differential top form omega sub T. And then this top form, of course, unique up to scalar. And the choice of this scalar usually relates to some scalar structure on this variety. And then standard Gauss-Manning connection theory, when you vary this T, then you obtain a function which is the integral of your family of, for each T, you have the corresponding function value. When you integrate over some cycles on your Calabi-Yau varieties. And this function f is conservation, don't again call such function periods in very vague sense. They satisfy a very precise equation which you can compute in the case of each Calabi-Yau variety. This equation are referred as Picard-Fuchs equation. First, I remind what this mum point condition, because it's important for me. This mum point means that in this point, monodromy of your differential equation has only one Jordan block. And this Jordan block is upper triangular matrix with 1, 1, 1, 1 on diagonal. And so you can always conjugate your monodromy to this triangular form with exponential coefficients over diagonal, 1 over 2 factorial, 1 over 3 factorial, up to 1 over k factorial, the sign of this matrix. And it means that locally your fundamental solution for your operator, these k functions, phi 0, phi k, they can be written in the following way. They can be, first function is always analytic, and the other functions, they are combinations. They are combinations with logarithm terms in different degrees. So the first will have logarithm degree 1, the second logarithm degree 2, and so on. So, and the first function, which is analytic, it is always have this form 1 plus t, c, it's a polynomial in t. So it's a good analytic solution for this. So I mean this coefficient f0. So our first function is important. It is always good. For example, such examples of this Picard-Fuchs equation for different Calabi-Yau, people studied many years, for example, for elliptic curve in the Legendre form with parameter t. You should integrate this holomorphic differential dx over y from 1 to infinity. You obtain the function f, because it depends on your t, it's a square root of this in differential, and it is almost straightforward to check that such equation annihilates your period. So theta square minus t over 1 minus t. So this equation has this very nice form. This is a typical Picard-Fuchs for elliptic curve. And this is the Calabi-Yau differential operator. For n equal 2, you have a K3 surface, you have one of the models. This model is usually called dwarf quartic. In dwarf model, they are all dwarf models. They have some degrees minus the product. So the dwarf quartic, it is a sum of degrees 1 to 4 minus t2 minus 1, x1, x2, x3. And it is not evident, but it is known now that there is a Picard-Fuchs, a differential operator, which is degree 3. And this, you have the product of t times 4, 4 theta plus 1, 4 theta plus 2, and etc. Similar situation with work quintic. If you have analog of this for threefold, this is a K3 surface, so it's a surface and it has dimension, complex dimension 2. And the next, the most important for mirror symmetry case of surfaces of threefold, the complex dimension 3, so the origin of Calabi-Yau, they should have complex dimension 3. So this is a special Calabi-Yau threefold with a special Hodge Rom with H21 equal to 1. Then Picard-Fuchs, it is also not evident, but it is well known since early 90s. It has the following form, which is similar to Picard-Fuchs, but it is degree 4. So theta to 4 minus 5 theta, 5 theta, 5 theta, etc. So these examples of my operators. What is good with this? The last operator, it is the most famous operator because it was the origin of so-called mirror symmetry theorem. First, it was some miracle in 91 when 4 physicists, Philippe Candelas, Xenia de la Ossa, Green and Parks, they considered this Calabi-Yau operator, the letter which corresponds to this threefold with quintic, work quintic, and they studied the Frobenius solutions of this operator. So analytic solution has this factorial hypergeometric form, and it was not evident from the very beginning, but all coefficients of this analytic solution, they belong to the series with integer coefficients. This integrality is a first a miracle. Second miracle, well, then they consider the second solution in fundamental solution, phi sub 1 with logarithmic term of degree in degree 1, and then this it is consequence of one point for this operator in 0, that this Frobenius basis has this special form. And the next correction term to logarithm, it is just this good series, but this good series has no more integral coefficients. This series has only rational coefficients. How to cure it? This Lian and Tian in 1996, they proposed the following procedure. And this is also some miraculous procedure. If we consider now the ratio of phi 0 and phi 1, the first two solutions of these Calabi-Yau operators, and take exponent of it, then we obtain a series in T, which starts with T, and all coefficients of this series Q of T, again, integer. So integrality is safe for this Q of T, and it starts from T. Then it means that it is invertible. So what they proposed? They proposed to invert this series and consider T like a function of Q. They call this Q canonical coordinate or mirror coordinate, and the corresponding inversion they called mirror map. And this mirror map, when you write it as a series in Q, is again non-integer. It has only rational coefficients. But when we derive solution to our operator in terms of this coordinate q and take the same procedure, it means take ratio phi 0 over phi 0, it's 1, phi 1 to phi 0, it's logarithm of q. So we have the series which depends on logarithm when second ratio gives you in degree 2. And coefficients of this are not integer. Then Liang and Yao said that let's apply to this rational series phi 2 over phi 0 in coordinate q. QDQ in degree 2 and denoted by y of q. They called it Yukawa coupling. And they killed this logarithmic term, and they, in the same time, they killed all non-integrality here. This u of q gives you a series with integer coefficient. So this Yukawa coupling, I will should say probably that it should relate to the Yukawa coupling in quantum cohomology, but I will not at the moment explain it. I just want to say that Q series in Yukawa coupling, you can again re-expand not in the degree of Q, but in the degree of Q to K, 1 minus Q to K. This is strange proposition. It is not so strange because it is very often people developed it. It is so-called Lambert series. They re-expand the power series in series of this Lambert expression. And the coefficients of this Lambert expression, they are fantastically up to division by 5. They are integer. They are again integer for this Yukawa coupling in Lambert series. Liang and Yao called this instanton numbers, and then they immediately understood that there is something famously known, namely the first two coefficients. It was even physicists discovered from their computations. They just made computations, the Candelas and company, and they said that the first number and the second number, it is very known numerological invariance. It is so-called Gromov-Witten invariance. And this Gromov-Witten invariance, they count number of degree k rational curves on our quintic threefold in P4. Well, in our case, it's just dwarf quintic, but in the theory of Gromov-Witten, you have a generic threefold of degree 5 in P4, and there is a classical question how many degree k rational curves lie on this threefold. And it was known since 19th century that number of line when k equal to 1, degree 1, it's 5 line. This threefold always contained. And second number was number of conic, and number of conic people computed only 100 years later. It was Sheldon Katz who computed it in 86. And of course, the third number, it was a physicist's prediction. They didn't know if it is true or not. But 2 years after their paper, Ellingrud and Ströme, they verified that it is indeed the number of rational qubits on this threefold. And they used computation with the equivariant localization formulas. But it was the other numbers. It was just conjecturally Gromov-Witten invariance. And mirror symmetry discovery of Giventhal and Liang, Yao, and Liu independently prove that these two sides of the story are the same. So these numbers obtained by physicists from the computation of coefficients of Lambert series for Yukawa coupling, and they are associated with one Calabi-Yau manifold. And if you take another Calabi-Yau threefold given by a degree 5 equation, then you have the same number of these rational curves or Gromov-Witten in another quintic in P4. So these two coincidences, they interpret like mirror symmetry theorem. And for this, Giventhal introduced this theory of quantum differential operators. So after that, of course, interest to Calabi-Yau differential operators arise enormously.
Excuse me, the previous page.
Stop.
The previous page. This, no. One, no.
Stop. No, it's not again this one. No.
Well,
Stop.
it was
This one.
no when there was the interpretation of the number nk. Oh,
This?
yeah. Yes, the number nk coincide. Yes, in blue. It is an observation or a general theorem.
No, I told you that these formulas, I mean these numbers,
Yes.
they were known. It means that people just in algebraic geometry, they computed the number of lines on generic degree 5 threefold, and
Yes.
it was 5.
Okay.
It was Schubert who computed it.
Yes.
And then people, Sheldon Katz again, compute number of conics. You see, it's highly non-trivial algebra geometric question.
Yes.
And then
I can imagine. Yes.
it was again Kontsevich and Manin hint that these numbers, I mean this numerology, coincides with Gromov-Witten invariance of holomorphic maps.
Okay, thank you.
And then it was a big fight who proved this theorem for in general. Giventhal or Liang, Liu, Yao, but finally decided that both. And then people started to find these Calabi-Yau differential operators, especially for n equal to 4, which correspond to the case of these triples. And there is a huge database which was constructed due to Gert Almquist, Van Enkelfort, Duco van Straten, and Vadim Zudilin. They first of all, they wrote some enormous table, and then Duco van Straten transformed this table in kind of computer package, which you can use if you find something which you think that it is Calabi-Yau. You can go to his database and to check by known parameters. But Calabi-Yau operators, they should all have regular singularities. They are always That's why, for example, it's immediately our Bessel is not Calabi-Yau. It's not Calabi-Yau because it has irregular singularity at infinity. It has t equal to 0 maximally unipotent monodromy point because of the structure of Frobenius basis special. It should be self-dual with respect to just conjugation, usual conjugation. And it should give the following integrality condition. So holomorphic solution should be integral. And this mirror trick with q coordinate given by ratio of exponent should be integral. And Lambert decomposition of q should give you analog of instanton numbers, analog of these instanton numbers. So if you have such operator, then you have a Calabi-Yau n equal to 4 operator. What also, as I told you before, if we take the analytic solution of Calabi-Yau, in some cases, this analytic solution can be explicitly computed with the help of residue theorem as a residue of this family of Laurent polynomials in denominators. So we have this parameter t, it's our function of t. We have this toric measure.
Well, I'm sorry. It is now 9 p.m. in Moscow. Do you have a lot of material more?
I have half of my talk.
Maybe we split it in 2 parts.
If you have nothing against it, I can.
Well, to me, it is interesting.
If it is interesting for you, I can continue because what I supposed to tell now, I suppose all this machinery to apply to Bessel.
Женя, вам интересно?
Мне интересно, но действительно можно было бы разбить.
Yes, of course. I think. Well, I have almost forgotten about the Bessel equation, and now, as I understand, we shall come back to it. Yes.
Yes.
So let us proceed next Wednesday. Being not in a hurry.
Okay.
Okay, agreed.
I agree.
Yeah, thank you very much. Well, I did not understand everything, but it is very interesting, and I'm eager to know how all this stuff relates to Bessel equation. So let's proceed next Wednesday. Yeah.
Iosif,
It's a good point to stop. By the way, Joseph, it's a good point to stop here.
Yes, yeah, that's what I thought. Yes. Sorry, Zhenya.
So I'm sorry I won't be able to join next Wednesday, but I will watch the recording.
Yeah, well, but it will be recorded, and you.
Yeah, I'll watch the recording.
Okay.
Jenny, I can tell you in Lille.
Okay, very good.
Thanks a lot. So we meet next Wednesday, the same time as always. Volodya, thank you and goodbye, and thank you.
Thank you for your patience.
Yeah, okay. Goodbye.